All right, so in this example, I want to solve a DE where involving a piecewise function. I kind of wrote over it, but I'll read that to you. So this is a first order DE. Our next example will be a second order one. Y prime plus y equals f of t, where f of t is equal to 1 when t is between 0 and 1, negative 1 when t is greater than or equal to 1. And it's an IVP, so we have this initial condition, y of 0 equals 0. So again, we're using Laplace transforms. If I took a Laplace transform of both sides of this thing, I'm going to get transform of y prime plus the transform of y equals. Now, what does the Laplace transform of this guy look like? Well, we talked about how to find the Laplace transform of piecewise functions by first representing them in terms of those unit step functions. So again, this piecewise function has this form to it, 1 here and negative 1 here. And so we're going to use this formula for determining what that function looks like. Okay? It's going to look like this. So g of t, which in our case is 1, minus g of t, 1, times our unit step function at t minus whatever a is. Remember, a comes from this. Also happens to be 1. Plus h of t, which is equal to negative 1, so that also looks like negative 1, times the same unit step function, u of t minus 1. Okay? Let's break this up. So this would simplify. Notice these are common terms here. So this plus this is equal to negative 2 u of t minus 1. And using my linearity property, we can write this as the transform of this 1, pull the negative 2 out, Laplace transform of u of t minus 1. Okay? Now, this side, we know that the Laplace transform of y prime would look like s y of s minus y of 0 plus this guy right here is equal to y of s. That's equal to the Laplace transform of 1, which we know is equal to 1 over s, minus 2 times. Now, what's the Laplace transform of u of t minus 1? Well, again, I'm going to find that page where we talked about it. I can show you. Okay. This fits this form from the previous video where we talked about how to evaluate the Laplace transform of some function f of t minus a times u of t minus a. Now, that function that's showing up there, we're not seeing one here, but I can think of it as the constant function 1. So if I think of f of t as being equal to the constant function 1, then f of t minus 1 is also the constant function 1. When you shift a constant function left to right, you have the same constant function. Okay, so that can be what my f of t minus 1 is here. Now, let's look again at what our theorem tells us we're supposed to do. So the unit step function tells me what that a is that's going to appear here. In our example, a is equal to 1, so I'm going to get an e to the negative 1s, or just e to the negative s there. And then f of t minus 1 is the constant function 1. And again, that tells us what the Laplace transform we're looking for is. So what is the Laplace transform of the function 1? Well, again, it's just 1 over s. Okay? So simplifying things down, my initial condition tells me that this is equal to 0, so I'll get rid of that. And then combining these terms, I'm going to get y of s times s plus 1 equals 1 over s minus, let's do this. Let's call this, actually, hold on, how did I write this before? I think I left it in that term. So I'm going to minus 2 e to the negative s times 1 over s. I'll just keep it in that form. Okay? I want to divide both sides by s plus 1 now, so I get y of s equals 1 over s times s plus 1 down here, minus 2 e to the negative s times 1 over s to the s plus 1. And then off to the side, we would need a partial fraction decomposition here. 1 over s to the s plus 1. That's an easy partial fraction decomposition, which I'm not going to go through the work for, but that would be equal to 1 over s minus 1 over s plus 1. Okay? So that allows us to, again, write that this way. 1 over s minus 1 over s plus 1. I can do the same thing here. I can represent this guy, because it's the same rational expression as this one, as 1 over s minus 1 over s plus 1. But then I can distribute this negative 2e to the negative s into both of those terms. So I'm actually going to get minus 2e to the negative s times 1 over s plus 2e to the negative s times 1 over s plus 1. Okay? Now I need to take an inverse transform of both sides. So y is equal to, the inverse transform of 1 over s is 1. The inverse transform of negative 1 over s plus 1, again, this is just from the table that we came up with in section 7.1, would equal e to the negative s. Okay, now let's take a look at this. So what is this thing here? This thing takes a familiar form. I've got to find my page again. Okay, we're taking the inverse transform of something of the form e to the negative s times a function of s. That negative 2 can pop out because of the linearity property. That is this. That's this form right here. Okay, and again, the f of t minus a that's appearing here is just, it's coming from the inverse transform of capital F of s. So what will that look like? The inverse transform of 1 over s is just the function 1. So f of t is equal to 1, which means f of t minus 1 is also equal to 1. And what we get is this, minus 2 times 1 from this guy times u of t minus 1. Remember, again, the 1 comes from the coefficient on that s right there. Okay? Now what about this guy? Plus 2, what's the inverse transform of this? Well, it would be e to the negative t, right? So in this case, f of t is equal to e to the negative t. However, again, coming back to this page here, once we identify f of t, we actually want our answer to include f of t minus a. So a, again, is equal to 1. F of t minus 1 then would equal e to the negative t minus 1, like that. Okay, so we need to make that shift. So that means we're looking at 2 times this guy, e to the negative t minus 1, put parentheses around that, times that unit step function, u of t minus 1. Okay? And there you have it. Whoops, I put an s here where I needed to put a t. Sorry, inverse transform, so it should have had a t instead of an s. But the rest of that should be correct. Okay, so that's one example. Let's do one more before we wrap things up for 7.3. Second order DE in this case. Now I'm doing the same thing, taking the Laplace transform of both sides of this guy. Because it's a second order DE, I have two initial conditions here, y of 0 equals 0, y prime of 0 equals 1. Let's take that Laplace transform though. So I'm going to get transform of y double prime minus 5 times my transform of y prime plus 6 times my transform of y equals my Laplace transform of u of t minus 1. Okay? Now notice we have found this Laplace transform already. We did that in the previous example. Laplace transform of u of t minus 1 ended up being, whoop, I'm showing you my notes, I'm showing you the wrong thing. Yeah, we did that here. So getting rid of that negative 2 there, we would have ended up with e to the negative s over s. So that's what we should be getting for this guy. This is equal to e to the negative s over s. Okay, just using a result we've already come up with. Now, let's work on this left-hand side. So the transform of y double prime is equal to s squared y of s minus s times y of 0 minus y prime of 0. And then this guy minus 5 times s y of s minus y of 0 plus 6 times y of s equals e to the negative s times 1 over s. Let's write that this way. Okay? Now, I need to work on this side. So y of 0 is equal to 0, which is nice because I lose a couple of terms by sending them to 0. Y prime of 0 is equal to 1. Okay, so this will be the constant negative 1 right here. All of my remaining terms have a y of s, so I can factor the y of s out of those. We get y of s squared minus 5s plus 6. Okay, then there's that minus 1 right there, and that's equal to e to the negative s times 1 over s. Okay, so I'm going to do a couple of things here. I'm going to add that 1 over, but I'm also going to factor this. I get y of s times, this will factor to s minus 2, s minus 3 equals 1 plus e to the negative s times 1 over s. Okay, divide everything by what we just factored there to isolate the y of s. That's equal to 1 over s minus 2, s minus 3, plus e to the negative s times 1 over s times s minus 2 times s minus 3. Okay, we need partial fraction decompositions for both of these. And again, as I've been doing for the sake of time and because we've done plenty of partial fraction decompositions, I'm going to jump straight to what they decompose to. You should be able to do these. These ones are not hard partial fraction decompositions to do. They're just a tad time consuming. So this guy right here, I'll write this over here, y of s is equal to, this one breaks down to negative 1 over s minus 2 plus 1 over s minus 3 plus e to the negative s times, this guy breaks down a little bit more complicated looking. It's going to be 1/6 over s minus 1/2 over s minus 2 plus 1/3 over s minus 3. Okay, so a couple of partial fraction decompositions there. Now we just need the inverse transform of both sides to solve this thing. So y will equal, this is the inverse transform of this would be negative e to the 2t plus inverse transform of that is e to the 3t. Okay, plus, now this thing, remember this takes the form of, let me find it here. Where are you? I have so many pages that I'm juggling around here. This thing takes the form of, not that page. Here we go. Of this. I'm taking an inverse Laplace transform of e to the negative a s times some function f of s. And this is where we can use that second translation theorem. So in this case, we're going to end up with the inverse Laplace transform of this guy. But because a is equal to 1, everything has to be shifted by 1. So the inverse Laplace transform of this would be 1/6 times 1, or just 1/6. Being a constant function, it doesn't really have any reason to shift. So we just have 1/6, or it doesn't have, it's shifting a constant function again horizontally doesn't change it. Here, this would normally be equal to minus 1/2 e to the 2t, but we need t to be replaced by a t minus 1 because of that shift. So that's t minus 1 there. This guy would normally be equal to 1/3 e to the 3t, but again, we have to replace our t by a t minus 1. And then we have our u of t minus 1 hanging out on the outside there. So that's from that second translation theorem. Okay? So that's a couple of DEs solved using these techniques. Hopefully that's enough to kind of get you through the homework. In section 7.4, we're going to look at a second part to this, more operational properties that sort of open it up to even more DEs that we can solve using Laplace transforms. But that's it for section 7.3.